We have seen in the previous lecture that there is no ultimate speed in Newtonian physics or Newtonian mechanics. We simply say that the speed of a particle may be infinity. But the Einstein's special relativity imposes a restriction on the upper limit of a speed of a particle. In accordance with special relativity, the highest speed of any signal or any information or any material particle must will be equal to the speed of light or electromagnetic wave in free space. It means speed of any particle v is always less or equal to c, although equal to has not been discovered till now. Always v is less than c. So the ultimate speed in special relativity is c, and you know the value of c is 3 into 10 to the power 8 meter per second. So according to special relativity, speed of any material particle can never be greater than 3 into 10 to the power 8 meter per second. Now let us try to explain this fact. Let us consider there is a particle at rest at the origin of our coordinate system, and we impress a constant force F on this particle in x direction. Since the particle is at rest and force is impressed in the x direction, so definitely the particle will start moving in x direction. And we consider that at any time t, the particle reaches to a point P where its velocity becomes v. Okay. Now we will try to find this velocity v at any time t. Okay. And for this we will write the equation of motion of the particle. You know that in a special relativity, mass varies with velocity. So when the particle was at rest at the origin, its mass was m0. But when it is at point P and its velocity is v, then its mass will be equal to m. And you know that this m is related to m naught by this relation m equal to m naught divided by 1 minus v square by c square root. Okay, m naught is called rest mass. Okay, now let us see how we can say that the ultimate speed in accordance with special relativity is c. It means speed is never greater than c. And for this we will write the equation of motion. And what will be the equation of motion? Equation of motion means Newton's second law of motion. Equation of motion. Let us write it. You know that the equation of motion is in fact dp by dt equal to f. Okay, where p is linear momentum at time t. And as I have told you that as the particle performs one-dimensional motion, so there is no need to write this vector sign. So equivalently we can drop the arrowhead over the quantities written here. So you can write the equation of motion simply in this form. Okay, and from here you can find what will be dp. This dp will be equal to f dt, and so integral of dp is equal to f integral of dt. And time varies from 0 to t, and at t equal to 0 the particle was at rest, so its momentum was 0, and we consider that at time t its momentum is p. Now let us see, this will be p equal to f times t. Okay, p equal to f times t. Now as you know that this p is equal to what? This is mv. So we will write instead of p mv, and mv will be equal to ft. Okay, but according to the relativistic mass variation formula, this m is equal to m naught divided by 1 minus v square over c square's square root, and this is equal to ft. And from here, from this relation, we have to find the value of v. So there will be some algebra. Let us square this equation both sides. So after squaring, what you will get? You will get that this is m naught square over 1 minus times v is also here. So this will be m naught square v square, and 1 minus v square by c square. This is f square t square. Now make the cross multiplication, and you can see our result will be what? This will be m naught square v square will be equal to f square t square times 1 minus v square over c square. Okay, and this can be written as m naught square v square equal to f square t square minus f square t square v square over c square. Now let us bring this last term in LHS, and you can see that we can take this m naught square v square as a common factor. So or simply you can take v square as a common factor. So this will be v square m naught square plus f square t square over c square. Okay, and this will be equal to f square t square, and therefore from here you can find the value of v. This will be what? This will be a square root of this much, so this will be ft divided by m naught square plus f square t square over c square and whole to the power half. Let us simplify this RHS a little bit. You can write it like this: ft divided by, let us take this f square t square and by c square as a common factor. So this will be what? This will be ft divided by c. Okay, and in inside the bracket there will be 1. Instead of this term I am writing here 1 plus m naught square c square and divided by f square t square and whole to the power half. And so this ft and this ft will cancel out, and v will be what? This will be c over 1 plus m naught square c square over f square t square. This is our result. Okay, so at any time t, the speed acquired by this relativistic particle is equal to this much. Now let us see what will happen when we will take t equal to infinity. It means after a very long time, what will be the speed? You are impressing the force for a long time, and guess what will be the speed? In Newtonian mechanics you have seen that speed becomes infinity, but here if t tends to infinity, then find the value of v. V will be equal to c divided by 1 plus 0, because here t is present, and when t will be infinity, the second term in the denominator will be 0, and this will be c. So surprisingly you can see that even after impressing the force for a infinite time, that is long time, 3 billion year of time, 100 billion of year of time, even after that the speed of the particle v becomes only c, not infinity. So from this result you can easily say that according to special relativity, speed of a particle will be never greater than c. You can apply the force for a long time. Even after that, speed becomes c, not greater than c. Okay, thank you very much.